Hi there and welcome back to Calculus of Variations. In this video I'm going to look at geodesics on a sphere. This is really an extension of the last video, which was geodesics on a cylinder. Now let's consider a coordinate system. So let's say that's our Z and that's our Y. Oh. Okay. That's our Y, that's our Z, and let's make our X here. Okay, that's X. Now, if we are looking to find the distance of the length of a small element on the surface of a sphere, then we start off in the same as the cylinder, and we'll note that a small segment ds squared would be equal to some dx squared plus dy squared plus dz squared. Now we've got to try and find these terms dx, dy, dz. Now this is similar to the cylinder, because if we were to draw, say, take a distance here, we'll call it r, okay, and we had rotated r in a circle, okay, so that's us on the xy plane. So if we imagine ourselves standing at this point here and we actually walked around the plane facing towards the y direction, we walked around the plane here, and let's say we walked to a point, say here, okay, then let us drop the perpendicular from there, okay, so we're going from there back to our x-axis. Oh, I'll just see if I can redo that and get it right. Okay, so we go from here and we drop it back to the x-axis. Okay, then in cylindrical coordinates we would have moved around a distance here, and that distance would have been our value of r and our angle, if I was to draw that in there, theta. So we'd have moved around a distance of r theta to get to this point here. Then in order to get to a point on the sphere, then we could turn around and face the y direction, and we could climb up along the face of the sphere. Okay, so now let's say I think what I'll do is I'll get rid of this line here, because I'm trying to cut out as many lines in this as I can, but you can see that angle theta there anyway. Okay, so now we're going to climb up the sphere in this ZY plane. Okay, just like climbing up some steps. So now we climb up the sphere, say like this. We're still on the surface of a sphere, and we note that as at some point on the surface of the sphere. So that would mean that we have walked in this plane here. Okay, so I'll draw that plane there. So we'll have walked in that plane there, a distance of r theta, and then we would have gone up a distance there. Now that distance we would have gone up, if I was to, let's say I dropped that perpendicular down, okay, there we go. Try to be careful of this so that you can see what's happening. Okay, so now I've climbed up that distance there on the ZY plane, and I'm still on the surface of the sphere there. Then we are able to say then from that that the distance up that we're going to come, now we've got to define an angle. Now we define the angle, that's angle phi, which is defined on the xy plane, but we define the angle theta. Now the angle theta is in the z x or the zy plane. It's this angle that the z-axis makes with this plane here. So we could pick this here, point here, okay, and I'll just draw it up like that, okay. So now we'll have come down an angle, okay. Now the angle would have come down, okay, if you continue that line from there up to there, again it's just on that plane, so that angle there all the way down would be our angle of phi, okay, so we'll call that angle phi. So that's the angle here, okay, there's the angle there, gets us to that point there. Now we're going to write these in terms of our x, y and z in terms of theta, phi and r, okay. So first of all, the easiest one to see here is if we were at this point here and we come up that distance there, okay, then we could say the distance along here that we've come, near that distance there, okay, we could say that y equals, now that there we could call r1, okay, I'll maybe try and write it there, okay, or maybe just put a wee sign out here, okay. Okay, so that line there, we could call that r1, okay. Now r1 is different from r, okay. R is the full distance to here, r1 is a shorter distance, okay. So r1 you could say equals, well sorry, let me just redo that. We could say that y equals r1 sine of phi, okay, so that distance there is the same as we come up here, this distance up here, okay, that's the angle it makes, okay, that distance there is the sine of this angle here, okay, so y equals r1 sine phi, but what is this r1? Okay, well that r1 we can write as r1 equals r, that's the r, okay, but it's the r sine of phi, okay, it's that angle there, so there we go, that's r1 equals r sine phi, okay, r equals r sine phi, okay. So then we'll be able to write y equals, and you place r sine phi in for r1, so y equals r sine phi, okay, r sine theta sine phi, okay. Now that's the equation we're looking for, and you can see it's similar to the cylindrical. The only difference in cylindrical is that in the z axis we just got a constant, so we just go straight up, but in the spherical system we have to cut in along the arc of the circle, okay, because we're on the face of a sphere. Okay, now you could do the same thing, and if you could look at that again, we would have a distance here, and we would be able to, we would come in from this angle along and then back up here. That would give us our value for our x. Now you can have a wee look and play about this yourself, and you'll be able to convince yourself that x equals, by the same argument, it would be, well, we'll call a distance r2. In this case, r2 would be, it would be this, let's see, r2 would be this distance in here. Okay, so it would be that distance there. Okay, so it would be r2 sine phi, and r2 would be equal r cos of theta. So you could write then x equals r cos theta sine of phi, and then you could say z. Now z is the height up. Well, z is just going to be the cos of this angle here. Remember, this is in the z plane. Okay, so this would be r cos phi. R cos phi. So then we would have our three equations that we were looking for. There's one there. Okay, and there's another one there. And that's our third equation there. Okay, so that's the three equations we were looking for. So now we'll be in a similar position we were in from the last video. We could then say ds squared equals dx squared, so we can differentiate this. Okay, but remember, this is a function of another function here as well, so there would be a product rule in there, and also for dy, and then we'd have to put a dz in, and we could mess about with it, and we could work out our value for our ds squared from the derivation. Now I'm not going to go through that derivation. You can find it online somewhere, and it's again pretty straightforward, and it doesn't add any value here right now to our calculus of variations. Now what's more useful, I think, is to have an understanding, an intuitive understanding of where the value of ds squared. So we can write ds squared equals, now it would be the same initially as of the cylinder. We would have our r d theta squared, which is what we have here, r d theta squared. That's one part of a triangle on the circumference of our circle. Okay, now the other part of the triangle and the circumference of our circle would be this distance here. Okay, now that distance there is going to be given to us by our, we're going to be taken from this point here, we're going to come up a distance. The distance we're going to come up is going to be r some value r excuse me, r d theta. Okay, but what is the value of r? Okay, well, we've already worked out earlier, this distance here is our r sine theta. Okay, so it's r sine theta, okay, times d theta. Okay, will give us this curve here. So we're going to have r sine theta d theta all squared. So you can derive that just from a bit of common sense and looking at the curve here. Okay, so we've got our r d theta as the curve here. Okay, where this is the r as the full radius, and there's our theta there on the xy plane. When we get to there, we have to come up here. Well, that curve there, if we run this down here, we've got our r sine theta is this distance here. Okay, so r sine theta is the angle. Sorry, r sine theta is this distance here, and the angle is d theta. Sorry, d phi. So we'll end up with r sine theta. Sorry, that should be d phi. Okay, d phi. Okay, because that's the angle here, phi. Okay, so you can see that you can work it out from just the geometry of the situation. So we're partly way there. Now what we can do is we can write this, and we could say ds squared upon the theta squared equals, so that would be r squared plus r squared sine squared theta times, now I'll write that as our phi derivative squared. So then we can write ds equals, and take out a common factor of the value of r, of course that's d theta squared, yeah, phi squared, yeah, okay, we take our d theta up, squared up, and we find the square root, and then we take out the common factor, which is going to be r and d theta, 1 plus sine squared theta phi derivative squared, all to the power of a half. Now we're ready to do our calculus of variations. Again, if we write down the functional, I would be the integral from some point A, B. Now this would be a function of our independent variable theta, okay, and independent variable, yeah, theta, okay. In this instance here, we have our phi as explicitly dependent on theta, okay. So phi derivative is explicitly dependent on theta, but there's no explicit dependence of phi, okay. So we can finish off like that and do that with integrate with respect to d theta. So it means that we can use a simplified version of the Euler-Lagrange. We can go partial f upon partial theta derivative equals some constant. Okay, now we'll just continue to do that now. So we'd have partial by partial phi derivative of 1 plus sine squared theta phi derivative squared to the power of half, and we can say that equals some constant k. And again, when we go through the differentiation, it's the same thing again. We're going to have half of this to the power of minus a half, and we're going to have differentiating this here, we'll have sine squared theta 2 phi derivative, and the 2's cancel out, so we'll end up with phi derivative sine squared theta upon the root of 1 plus sine squared theta times phi derivative squared, and we know that there equals some constant k. Now again, we're going to solve this for our value theta derivative. Okay, that's theta derivative squared. For theta derivative, okay, so I'll just write solve for, so I should say phi derivative. Now, I'm not going to go and do this, the algebra here, but it's the same thing again. We can take this up here, multiply it by the k, we can square this to get rid of the square root, and then we can take our values of phi derivative over here again and gather all the phi derivatives together. Okay, on this side. Okay, so you would end up with, and again, check this for yourself, phi derivative equals k upon sine theta, the root of sine squared theta minus k squared. Okay, so this would then, if we took the integral of these, would be the integral of d phi would be the integral of k upon sine squared, that should be, let's see, derivative. So what we'll do here, is same as previous, we'll take out a factor of the sine here, okay, so you end up with a sine squared theta, because you're just trying to knock this into the same kind of standard form of root 1 minus k squared upon sine squared theta all by d theta. Okay, we're just taking a sine squared out of the square root. Okay, so again, we want to try and get this into some kind of standard form. Now, to simplify this a bit, just to make it look a bit simpler, we'll replace this 1 upon sine squared by cosec squared. So we'll have integral d phi equals the integral of k, and this 1 upon sine squared, we'll call that cosec squared theta upon 1 minus, and that's going to be the root of 1 minus k squared cosec squared theta by d theta. Now, the standard form we're trying to get it into is the same as the previous video, 1 minus 1 upon the root of a squared minus x squared by dx would equal inverse cos x upon a. Okay, that's the integral of that, would equal that. So that's our standard form. And we're trying to get this here into that standard form. And again, we can use a substitution, and the substitution we're going to use is u equals cot theta, okay, because then we know that du will equal minus cosec squared theta d theta, and we also know the trig identity that cosec squared theta equals 1 plus cot squared theta. Okay, so it means that we can rewrite this here, if we can squeeze it in there, we can rewrite this here as the integral of d phi equals the integral of, well, we need a minus sign so the two minuses cancel out when we do this sign, minus sign has to cancel out this minus sign in order to make it positive. So it's minus k, and in place of the cosec squared we can put in du, so that's cosec squared d theta, cosec squared d theta becomes du all upon the root of 1 minus, and this will have to be in the form k squared 1 plus u squared, okay, all by d theta, well no, not by d theta, it's all by du, okay. So you can just, if you multiply that out, you'll convince yourself that we need it in this form in order to get this, in order to get it in the correct standard format. Okay, so that can be then rewritten. If I can get to the next line, hopefully I can squeeze it on this page. We can then write that as, I'll just go for this end here, integral of, now we'll just get rid of the k, so we can call that minus du, okay, upon the root of, that's right, okay, the root of a squared minus u squared, okay, now that's going to equal inverse cos u upon a, okay. Now in this instance here, a is going to equal root 1 minus k squared upon k. So that there is going to equal, when we integrate this here, we could, that would make it phi minus the phi naught, okay. Now almost there, so now we can write that there, and we can say that cos of phi minus phi naught equals cot theta, well, equals, what we can do is equals u upon a, okay. Now there's u there, u is cot theta, okay, and so it would be cot theta upon a, so we can take the a up here, that would be the a up here, and that there is the equation of a plane in spherical coordinates, okay. Right, so that's what we've been looking for since the start, okay. So Now, if I move on to, I'll move on to the next page, and I'll show you that that's the equation of a plane. Okay, and if I pop it onto the next page, I'll show you that that is the fact equation of a plane. If we were to note the planar equation of a plane would be, planar equation of a plane would be ax plus by plus cz would equal 0, and we know our value of x from the previous page would be a, and it would be r cos phi sin theta plus b r sin phi sin theta plus c r cos theta equals 0. So we can get rid of our values for r, and we can take the cos theta across to the other side, okay, and then take out our value of sin theta as a common factor. So you'll end up with a cos phi plus b sin phi all times sin phi would equal minus cos of theta, sorry, that's going to be sine of theta. Okay, that's a common factor, sine of theta I've taken out. Okay, now we can then write that there as a cos phi plus b sin phi equal, to take the sin theta down, that becomes minus, there's a term for c, it's actually, yeah, c, I would just, yeah, c, it's a constant there, okay, from our c here, okay, so it would be minus cot theta, right, times c, okay. In this instance here, our c there would equal the inverse of the other one, which would be k upon root 1 minus k squared. Okay, so now we can rewrite this using a bit of standard trig. We could write it as let's see, it was a cos phi plus b sin phi equals, now we could write that as the same way we could write it as the square root of a squared plus b squared times a upon root of a squared plus b squared cos phi plus b upon root of a squared plus b squared sine of phi. Okay, so that's exactly the same. That line there is exactly the same as that line there. That cancels out with that, and that cancels out with that. You end up with the same thing. But this thing here is equal to our value of cos. Okay, so this one here is going to end up our value of cos, and we'll call it phi naught, okay, to distinguish it from our value of phi. So we could rewrite that there as the root of a squared plus b squared times cos of phi naught, cos of phi, plus, and this here would be the sine of phi naught, sine of phi. Again, just put that into a little triangle and put AB and A and B on one side and a squared plus b squared on the other, and you'll see that that there will give you your cos and that there will give you your sine. Okay, so then that there can then be written as, you could say that A cos phi plus B sin phi equals the root of A squared plus B squared, okay, times the cosine of, and that would be phi minus phi naught, okay. Right, so that can be written as that, okay. So now if we put that back into our original equation, then we can say that the root, almost there, root of a squared plus b squared cos of phi minus phi naught equals our value minus cot theta times c. Now if we take these values of c over and we create just one constant, okay, one value, and we just call it a, then we would end up with a cos phi naught, sorry, phi, yeah, that's right, phi minus phi naught would equal cot theta, okay, and the negative side is taken in with this value of a. Okay, so we put a line there, and we can see that that indeed is the equation of a plane. Okay, so that equation there is, if I can turn that off and this one's on, is the same as the equation that we were looking to find out. Okay, so that really finishes this video, and it gives you the proof of the geodesic on a sphere. The geodesic on a sphere is created by a plane through the origin that maps onto the circumference of a sphere. Okay, thank you for listening, and I'll get you in the next video. Goodbye.